Welcome back, everybody. This is AP Chemistry. We're in Unit 12 and Section 1, taking a look at some factors that affect the thermochemistry along the way. Chemical reactions are driven by two factors, okay? We want to keep these in mind as we're working with the problems. There's an energy factor that many spontaneous reactions proceed with a decrease of energy. That means that almost all exothermic reactions are spontaneous, and most phase changes are endothermic, yet they are spontaneous. So if we take a look at water in its solid form or ice, it goes into a liquid form pretty much spontaneously. It just needs just a little bit of environmental energy, only 6 kilojoules of energy to go in. Some reactions, though not spontaneous on their own, they can be given, can be convinced, if you will, to proceed if we have a high enough temperature. So calcium carbonate can actually decompose into carbon dioxide gas as well as calcium oxide if we have enough energy to go, and that energy would be 1100 Kelvin. Okay, that would actually get it to go. Now, another factor that would be driving these chemical reactions would be what we consider to be the randomness factor. Nature tends to move spontaneously from a state of lower probability to higher probability with this. Okay, so what that means is we can go from more ordered to a more random state. And think about the different states of matter of all types of matter. We have a solid where all the particles are stuck together and really tightly, while a little bit more fluid with the liquids and really spread out with gases. Entropy is the measure of that randomness factor. That's what entropy is, the measurement of that randomness factor. So we can see if something is going to be spontaneous or non-spontaneous, or even predict it based on those given things. And so we just take a look at the final minus initial. If we end up with the final state being a negative, then it's not going to be a spontaneous thing. My final factor would be my entropy would be spontaneous if my final ends up being a positive number. Okay, so a liquid would have, these are the factors that would influence that. A liquid would have higher entropy, and then we would see that I would have a gas even higher than that, and that's because of the movement of those particles, right? Also, what affects the particles would be the temperature that those particles are in. Adding in temperature, especially in phase changes, adding in temperature would increase the collisions, which increases that randomness, okay? So we would take a look at some scenarios and see whether this is going to be a positive or negative. Let me just put up all three scenarios here to just predict whether this is going to be happening, and let's apply our rules as we go. All right, so we're going to be taking a look at taking dry ice, and it's going from dry ice. This is carbon dioxide as a solid, and we're putting it from negative 80 going to room temperature. Okay, so if we're allowing it to warm to room temperature, we're increasing the temperature. And so if we increase the temperature, the question is, would that be going to a gas? I would expect that to be a positive S, or a positive entropy, because it's a solid to a gas and we're increasing temperature. Now we have dissolving bromine in hexane. Now bromine in this case, bromine typically is going to be a liquid, but if they're saying dissolving, we would assume that it's going to be like a solid particle in this one. And also bromine is going to be nonpolar along with my hexane, so that's going to be nonpolar. I would expect that to be a positive entropy as well. Now condensing gaseous bromine, okay, so this is gaseous bromine down to a liquid bromine. Well, that's going the opposite direction, right? Remember that gas is higher entropy than the liquid, so we would expect this to be a negative in this case, because gases have a higher entropy value than our ending product, which would be my liquid bromine, okay? That would give me a negative value. All right, so if we're going to be calculating this out, this you're going to find is actually pretty simple. We're going to be calculating for the following reaction, and we would consult some of the charts with this, okay? So these are going to be the entropy values that we're going to be using here. Calcium carbonate, if I look it up, that's going to be a 92.9, and that will be in joules per mole times Kelvin. All of these values are going to be in joules, and that's going to be significant a little bit later on. Calcium oxide is going to be 39.8 joules per mole times Kelvin, and then carbon dioxide, a much higher value because it's a gas, 213 joules per mole times Kelvin. Okay, so if I'm going to be using the equation, I would see that my delta S is going to be the sum of the products, and so that's going to be a 39.8 plus my 213.7, and that's going to be minus my reactants, which is a 92.9. If I just add that all up, I'm going to end up with a positive 160. Positive 160.5. I'm having troubles here today, folks. And that's going to be joules per mole times Kelvin. And so I'd see it's positive, and so then it is going to be spontaneous. Just because I can't write doesn't mean that we can't interpret it. That's a 160.5. All right, so that's all we need to be doing. Pretty easy problems. I don't think you'll have any problems with that, okay? Now, a reaction that results in an increase of moles of a gas is accompanied by an increase in entropy. If the gas molecules decrease, we would expect that it's going to be going down in value. That's a negative number. Okay, so let's take a look at 1 mole of calcium hydroxide in water. And for this, we're going to want to do a balanced equation. And this is where we get our solubility rules as well. So we take a look at calcium hydroxide. And the question is this going to be soluble? Well, we use these values. Yes, there are charts for it, but I would see we have 2 hydroxide off of this, and this is going to be aqueous. And so I look up my values. This is 83.4. This is going to be 74.8. And then this is going to be 34.8. Now keep in mind, my delta S is the sum of those parts. So that's going to be my 74.8 plus 2 times 34.8 minus my 83.4. Okay? And so I'll end up with a value, a delta S, of a positive 61 joules per mole times Kelvin. Okay, so that would be, this would be spontaneous. Okay, so that is going to be soluble. That's what we're doing. And so that's why you see on those weird charts, sometimes you'll see partially soluble or, things like that. It's because of the values there. It's more quantitative than that. Let's take a look at the combustion of methane. Now, methane itself is CH4. And so the question is that thing going to be spontaneously combustible? To combust it, I need O2. We're going to get CO2 plus H2O. And to balance this all out, we'll need 2 and 2. So looking at my values for this one, let's see, I lost my spot. Okay, here we go. I see that my carbon dioxide is 213.6, and I see that my 2 waters is going to be 139.8, and this ends up being 186.2, and this is going to be 410. Okay, so I take this side, add that up, and I subtract off my 186.2 minus my 410, plus my 410, and so I'll end up with an answer of negative 242.8 joules per mole times Kelvin. Okay, that's going to be less gas formed, and I have a negative value. This is non-spontaneous. Okay, since it's a negative in there, negative 242.8, non-spontaneous, that means that methane doesn't just sit out there and combust on its own. Okay, we do have to add an ignition source to get it to go. Okay, that's all we need to be doing with that. Pretty straightforward. Now, there are 2 quantities that are going to also affect this: enthalpy, entropy, and your Gibbs free energy. Okay, Gibbs free energy is the portion of the total energy change that's available and or free to do the useful work. If I have a positive Gibbs free energy, energy must be supplied. It's endothermic. And if I have a negative Gibbs free energy, it's released for work. Okay, that's going to be a product. That's exothermic. Okay, now just keep those things in mind, and then we take a look at those things all together. All 3 of those factors is going to be how we do this. Now, when using the Gibbs-Helmholtz equation, the Helmholtz equation is just taking all these factors into there. Just to keep in mind a couple of things, T must be in Kelvin. Okay, and then my delta S, now this is the biggest one because our values were in joules, must be in kilojoules. Okay, we've been using joules all along with this, and so just keep that in mind as we're using this equation of those units along the way. Okay, to this point, the sign will determine that spontaneity. Again, if it's a negative, it is spontaneous. If it's positive, then it's not going to be taking place. Okay, it is conceivable to have a Gibbs free energy of 0. That means that the system is at equilibrium. There are a couple factors that tend to make this a negative delta G, and it's a negative delta H or a positive delta S. Okay, physical changes, entropy is the major driving force. Okay, so let's take a look. If we're at the standard free energy change, first of all, 1 molar and 25 degrees Celsius and 1 atmosphere, let's take a look at this reaction, and we're going to calculate out my delta H, my delta S, and the delta G. It looks like a big daunting thing, but it's really not, guys. Just keep track of these as we go. I'm going to look up some values, my calcium sulfate, and it's more being a good record keeper. Okay, my delta H value is going to be a negative 142.0. My delta S value is going to be a 106, and they even give me a delta G value of negative 104.0. Okay, that's my calcium sulfate. My calcium ion is a delta H of negative 542.7. My delta S is going to be a 71.9, and my delta G is going to be a negative 552.0. And then lastly, I have my sulfate. My delta H is given to be a negative 909.3. My delta S is given to be a 213.7. And my delta G is given to be a negative 745.0. Okay, now let's calculate this out using this Gibbs-Helmholtz equation. Okay, so first of all, I need to find my delta H, don't I? If I'm going to use this equation, I've got to find these individual variables. My delta H is going to be my, let's see, I have negative 542.7 plus a negative 909.3. That's my sulfate as well as my calcium ion. And we're going to be subtracting that from a negative 142. That's my calcium sulfate. So my delta H gives me a negative 1310, and that will be in kilojoules. Now let's take a look at my delta S. Okay, again, my calcium and my sulfate, that was a 71.9 plus a 213.7 minus my 106. So my delta S ends up being 179.6. Now be careful because that's in joules. So that will be 0.1796 kilojoules. Now if I calculate out my delta G, I'll have my delta H minus my temperature times my delta S, and that needs to be in kilojoules. So let's plug in my values. I have a negative 1310 minus my 298 times 0.1796, and that's in kilojoules. My delta G ends up being a negative 1363.5 or thereabouts. Okay, that would be, if it's a negative value, that is going to be spontaneous. All right, so that's all I needed to be able to do for those. And really, it's easy math. It's just a matter of keeping track of your different variables along the way. Okay, now to a good degree of approximation, the temperature variation can be neglected. Okay, this means that to apply the Gibbs equation to temperatures other than 25, you just need to change that value of the temperature. So that's not too bad. Let's take a look at an example of what that would look like when I have reaction of 1 mole of iron 3 oxide with hydrogen. Okay, so I'm going to take iron 3, Fe2O3, plus 3 hydrogens, and that will give me 2 irons and 3 waters. Okay, so looking at this, my delta H ends up being a negative 824.2. My delta S, that would be 87.4. And my delta G value, again, just from the charts, negative 742.2. Okay, looking at my hydrogen, well, my delta H is 0 because that's its state of the element. My delta S, that is a 130.6. And my delta G is also 0 because that's its state in its natural form. Look at my iron, my delta H, that's its state at natural form. Okay, so that's a 0. My delta S, that's going to be 27.3. And my delta G, again, is the elemental form, so that's a 0. Now we look at the last one is going to be my water. Negative 241.8 is my delta H. My delta S is going to be 188.7, and my delta G ends up being negative 228.6. Okay, so let's keep this all straight. All right, let's do my delta H first. That will be, let's see, and let me put a bracket here. Let's do my iron first. Well, it's 2 times my iron, which is 0, plus my 3 times my water. Okay, so that's there. Minus my 1 times my iron 3 oxide plus my 3 times my hydrogen. Okay, if I just plug all those values in, I'm going to get a value of delta H equals 998.8 kilojoules. Okay, let's do the same thing with my delta S. This is going to be now 2 times 27.3 plus 3 times 188.7. That's a bracket there. Minus my 1 times 87.4 plus my 3 times 130.6. My delta S ends up being 0.1415 kilojoules. So my delta G then, now remember, temperature is a little bit different too, isn't it? I have 98.8 minus 503 Kelvin times 0.1415 kilojoules. And so that will end up being positive 27.63. This means, since it's positive, non-spontaneous. That seems like a lot of work. But if we just take a look at it in turn, keep track of those things, it's really not that bad, okay? A couple more. We take a look at at 335 Kelvin. We're going to see if it's spontaneous or non-spontaneous. Okay, I'm just going to go the fast route, just using those tables. I'm going to get my delta F, or delta H, I should say, of the formation. That's going to equal negative 238.70 minus negative 110 plus 0, because this is the elemental state. That will give me negative 128.2 kilojoules. My delta S is going to be in 0.1268 kilojoules minus 1976 plus 2 times 0.1306. That will give me a negative 0.332 kilojoules. So my delta G is going to then be, at 335 Kelvin, is going to be negative 128.2 minus 355 times negative 0.332. That gives me a negative 10.3 kilojoules. Okay, just remember that you got to convert this into kilojoules when you're doing the math. Therefore, since this is negative, this is spontaneous because it's a negative 10.3. Cool. So now we're seeing the flow of this, and this really isn't that bad. It seems daunting when you take a look at it until you just plug in your values. Now here we have two things that are in their natural states, right? So those values are going to be 0, and so we can go through this pretty quickly. My delta H of formation is going to be 2 times my 90.2 minus basically 0 plus 0. Okay, so I'm going to get 180.4 kilojoules. My delta S is going to be 2 times 0.2107 minus 0.1915 plus 0.205. That's going to be my nitrogen and my oxygen, and that will give me 0.0249 kilojoules. Okay, you ended up with 24.9, but that is 0.0249 kilojoules. So now let's take a look at my delta G at 335 Kelvin. Okay, I'm going to get 180.4 minus my 355 again times 0.0249 kilojoules. And so I'll end up with a value of positive 171.6 kilojoules. Since it is positive, it is non-spontaneous. Okay, so pretty straightforward. Just look up your values, and I think you got everything you need to do for the rest of your problems. All right, good luck.